Look up on a dark night, away from the glow of cities, and you can see it with your naked eyes. A faint, luminous band stretching across the sky from horizon to horizon, a river of soft white light that has been visible to every human being who has ever lived under a clear, dark sky. The ancient Greeks called it Galaxies Kyklos, the Milky Circle. The Romans called it Via Lactea, the Milky Road. In Hindu mythology, it was the celestial Ganges. The Cherokee saw it as the path where a dog had scattered cornmeal across the sky. The San people of southern Africa called it the backbone of the night. Every culture that has looked up has seen it, named it, told stories about it. And every culture got the same thing wrong. They thought it was something painted on the sky, a feature of the heavens, a celestial decoration. They could not have known that they were looking at their own galaxy from the inside, that the faint band of light was the combined glow of billions of stars, too distant and too numerous to be seen individually, all arranged in a vast, flat, rotating structure, and that they were embedded within that structure like a grain of sand embedded in a spinning disk. The first person to understand what the Milky Way actually was, or at least the first to point an instrument at it and see the truth, was Galileo Galilei. In 1610, he turned his small, crude telescope toward the Milky Band and saw something that no human eye had ever resolved. The smooth globe broke apart into stars, thousands of them, tens of thousands. The Milky Way was not a cloud or a streak of celestial milk. It was stars packed so densely and so distantly that the unaided eye blurred them into a continuous wash of light. Galileo reported this in his Sidereus Nuncius, the starry messenger, and it was one of the many observations in that slim book that began to dismantle the old picture of the cosmos. But even Galileo did not fully grasp what he was seeing. He knew the Milky Way was made of stars. He did not know that those stars, together with the sun and every other star visible in the night sky, formed a single enormous structure, and that the band of light was the view along the plane of that structure, where the stars were most densely packed along the line of sight. That insight came later, piecemeal, over centuries of painstaking observation and argument. In the 1780s, William Herschel, the German-born musician turned astronomer who had already discovered Uranus, attempted the first systematic survey of the Milky Way's shape. His method was simple in concept, if brutal in execution. He counted stars in different directions, hundreds of sample fields across the sky, and assumed that more stars in a given direction meant the galaxy extended farther in that direction. The result was a rough map, a flattened, irregular shape with the sun somewhere near the center. Herschel's map was wrong in important ways, most critically in placing the sun at the center, but it established something revolutionary, the idea that the stars were not scattered randomly through infinite space, but were organized into a finite, structured system with a definite shape. The Milky Way was not just a visual phenomenon. It was a physical object, a thing with boundaries and geometry, and we were inside it. For the next century and a half, astronomers argued about the size and shape of this thing. The arguments were hampered by a problem that would not be fully understood until the 20th century: interstellar dust. The space between stars is not empty. It contains vast clouds of gas and microscopic solid particles, dust grains made of carbon, silicon, iron, and other elements, and this dust absorbs and scatters starlight. Stars seen through dust appear dimmer and redder than they actually are, and in some directions the dust is so thick that it blocks visible light entirely. This means that when you try to map the galaxy by counting stars, you systematically undercount in directions where dust is thick, which happens to be along the plane of the galaxy itself, precisely where you most need accurate counts. The dust fooled astronomers for generations. It made the galaxy appear smaller than it was and made the Sun appear to be closer to the center than it actually is, because the dust hid the more distant stars on the far side of the galaxy, making it seem like there were roughly equal numbers of stars in every direction. The first person to correctly determine the Sun's position within the Milky Way was Harlow Shapley, working at the Mount Wilson Observatory in the 1910s. Shapley studied globular clusters, dense spherical collections of hundreds of thousands of old stars that orbit the galaxy like bees around a hive. He measured the distances to these clusters using Cepheid variable stars, the same cosmic yardsticks that Hubble would later use to measure the distance to Andromeda, and he mapped the distribution of the clusters in 3 dimensions. What he found was striking. The globular clusters were not centered on the Sun. They were centered on a point tens of thousands of light years away, in the direction of the constellation Sagittarius. Shapley concluded correctly that this point was the true center of the Milky Way and that the Sun was located far from the center out in the galactic suburbs. This was a Copernican moment for galactic astronomy. Just as Copernicus had displaced Earth from the center of the solar system, Shapley displaced the Sun from the center of the galaxy. We were not at the hub. We were peripheral, ordinary, unremarkable in our location. The galaxy had a center and we were not it. Shapley's estimate of the galaxy's size was too large, roughly 300,000 light-years across, about 3 times the modern value, because he did not fully account for the dimming effect of interstellar dust. But his fundamental insight that the Sun orbits far from the galactic center was correct and remains one of the key facts about our place in the cosmos. So what is the Milky Way exactly? What would you see if you could somehow travel far enough away to look back at it from the outside? You would see a barred spiral galaxy. That classification contains 3 important pieces of information, and each one tells you something fundamental about the structure you live in. First, it is a galaxy, a gravitationally bound collection of stars, gas, dust, and dark matter, held together by its own gravity, orbiting a common center. This distinguishes it from smaller structures like star clusters and larger structures like galaxy clusters. The Milky Way is a single coherent system, a city of stars in which every member is gravitationally linked to every other member. Second, it is a spiral. If you could see it face on, looking down from above the galactic plane, you would see a pattern of bright, curving arms winding outward from the central region like the arms of a pinwheel. These spiral arms are not solid structures. Stars do not stay in them permanently. The arms are density waves, regions of compression that move through the disk of the galaxy like sound waves moving through air. As gas and stars orbit the galactic center, they periodically pass through these denser regions. The compression triggers the collapse of gas clouds, which ignite star formation, and the bright young stars that result, blue and luminous and short-lived, illuminate the arms, making them stand out against the dimmer background of older stars. The spiral arms are visible because they are where the newest, brightest stars are being born. The older, redder stars between the arms are still there, still orbiting, but they are less conspicuous. The arms are not the bones of the galaxy, they are more like the crests of waves, patterns that move through the galaxy at a different speed than the stars themselves. Third, it is barred. The central region of the Milky Way is not a simple spherical bulge. It contains a bar, an elongated structure of stars stretching across the center, roughly 27,000 light-years long, oriented at an angle of about 25 to 30 degrees relative to the line connecting the Sun and the galactic center. The bar rotates as a rigid structure, and the spiral arms emerge from its ends. Barred spirals are actually the most common type of spiral galaxy in the universe. About 2/3 of all spiral galaxies have bars, and the Milky Way is among them. The bar was difficult to detect from our position inside the galaxy, and its existence was not confirmed until the 1990s and 2000s through infrared surveys that could penetrate the dust obscuring the galactic center. The Spitzer Space Telescope, observing in infrared light that passes through dust much more easily than visible light, provided some of the most convincing evidence for the bar's existence and helped to determine its size and orientation. Now let me walk you through the structure of the galaxy from the inside out, because the Milky Way is not a simple object. It has multiple components, nested within each other, each with its own characteristics, its own population of stars, its own history. Start at the center. The very heart of the Milky Way, in the direction of the constellation Sagittarius, about 26,000 light-years from the Sun, is a region of extraordinary density and violence. The innermost few light-years contain a dense cluster of stars orbiting at tremendous speeds around a single point. Sagittarius A star, a supermassive black hole with a mass of about 4.15 million times the mass of the Sun. This black hole was identified through decades of painstaking observations. In the 1990s and 2000s, two independent teams, one led by Andrea Ghez at UCLA and the other by Reinhard Genzel at the Max Planck Institute, tracked the orbits of individual stars near the galactic center using adaptive optics, a technology that corrects for the blurring effect of Earth's atmosphere in real time. They watched stars whipping around an invisible point at speeds of thousands of kilometers per second, completing full orbits in as little as 16 years. One star, called S2, was observed to approach within about 120 astronomical units of the central object, roughly 3 times the distance from the Sun to Pluto, moving at nearly 3% of the speed of light. The orbits allowed a precise measurement of the central mass, 4 million solar masses, concentrated in a region smaller than our solar system. The only object that can contain that much mass in that smaller volume is a black hole. In May 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a glowing ring of superheated gas surrounding a dark central shadow. The image confirmed what the orbital studies had established. At the center of our galaxy sits a monster, an object so dense that space-time itself curves around it and closes off a region from which nothing can escape. The black hole is not currently active in any dramatic sense. It is not consuming large amounts of matter. It is not powering luminous jets or quasar-like emissions. Sagittarius A star is, by the standards of supermassive black holes, remarkably quiet, accreting matter at a rate millions of times below its maximum capacity. But it has not always been quiet. Observations of structures called Fermi bubbles, enormous lobes of high-energy gas extending above and below the galactic plane, suggest that the black hole underwent a period of intense activity, perhaps 2 to 4 million years ago. The ancestors of modern humans were already walking upright in Africa when the black hole at the center of the galaxy last roared. Surrounding the central black hole is the galactic bulge, a dense, roughly spherical concentration of stars extending about 10,000 light-years from the center. The bulge contains some of the oldest stars in the galaxy, many of them more than 10 billion years old, formed when the Milky Way was young. These stars are predominantly red and orange, cool and dim, having long since burned through their hydrogen and settled into their late evolutionary stages. The bulge also contains younger stars and active star-forming regions, particularly in the dense molecular clouds near the galactic center, but the overall population is old. The bulge is not smooth. It has a boxy or peanut-shaped structure when seen from the side, a shape produced by the dynamics of the central bar. Stars in the bar execute complex orbits that, over time, puff the bar up vertically, giving it a thickened X-shaped profile when viewed edge-on. This shape has been mapped through surveys of red giant stars and matches the predictions of computer simulations of barred galaxies. Extending outward from the bulge is the disk, the most recognizable feature of the Milky Way and the structure that produces the band of light we see in the night sky. The disk is where we live. It is a flattened, rotating structure, roughly 100,000 light-years in diameter and about 2,000 light-years thick in the region near the Sun. Though the thickness varies and the disk flares outward at its edges, recent studies using data from the Gaia Space Telescope, with faint stellar populations extending to 200,000 light-years from the center, the disk contains the majority of the galaxy's gas and dust, concentrated primarily in the spiral arms and in a thin layer near the midplane. This gas, mostly hydrogen with about 25% helium and traces of heavier elements, is the raw material for star formation. Where the gas is densest and coldest, it collapses under its own gravity to form new stars. The spiral arms are delineated by these regions of active star formation, traced out by the brilliant blue light of hot, young, massive stars that live fast and die young, exploding as supernovae after only a few million years. These short-lived stars never travel far from their birthplaces before they die, which is why they remain concentrated in the arms where they were born, highlighting the spiral pattern. The disk itself has two distinct components. The thin disk, where most of the gas and young stars reside, has a scale height of about 300 to 400 light-years, meaning that the density of stars drops by about a factor of 3 for every 300 to 400 light-years you move above or below the midplane. The thin disk contains stars of all ages, but is dominated by relatively young and middle-aged stars with relatively high abundances of elements heavier than helium, what astronomers call metals, even though most of these elements are not what a chemist would call metals. This terminology is a source of endless confusion and occasional amusement, but it persists because astronomers adopted it long ago and refused to change. Surrounding the thin disk is the thick disk, a more vertically extended population of stars with a scale height of about 1,000 to 1,300 light-years. The thick disk stars are older, typically 8 to 12 billion years old, and have lower metal content than thin disk stars. They orbit the galactic center with slightly different kinematics, moving with more random eccentric orbits compared to the more orderly circular orbits of the thin disk population. The thick disk is thought to have formed earlier in the galaxy's history, possibly through a different process than the thin disk. One possibility is that it represents an earlier phase of star formation before the gas had settled into a thin, orderly disk. Another possibility is that it was created or thickened by ancient collisions with smaller galaxies, their gravitational disturbances puffing up the early thin disk and scattering its stars into higher orbits. The Gaia satellite, which has measured the positions and velocities of nearly 2 billion stars with unprecedented precision, has provided evidence that at least one significant merger event, sometimes called the Gaia Enceladus or Gaia Sausage merger, occurred about 8 to 10 billion years ago, when the young Milky Way collided with and absorbed a smaller galaxy. The debris of this ancient collision is still visible in the form of stars on highly elongated orbits that cut through the disk at steep angles, ghosts of a galaxy that no longer exists as an independent entity. The disk is not perfectly flat, it is warped. If you could see the Milky Way edge on from a great distance, you would notice that the outer edges of the disk bend upward on one side and downward on the other, like a slightly twisted vinyl record. This warp has been known since the 1950s from radio observations of hydrogen gas, and its cause has been debated for decades. The most likely explanation is the gravitational influence of the Milky Way's satellite galaxies, particularly the large and small Magellanic Clouds, which orbit the Milky Way and tug on its outer disk as they pass. Recent studies suggest that the Sagittarius dwarf galaxy, a small galaxy currently being torn apart and absorbed by the Milky Way, may also contribute to the warp. The disk is also corrugated, with ripples that may have been excited by the passage of the Sagittarius dwarf through the disk. Beyond the disk, extending in all directions, is the stellar halo. This is a vast, roughly spherical cloud of stars surrounding the galaxy, extending to at least 300,000 light-years from the center, and perhaps much farther. The halo contains only about 1% of the galaxy's stars, but it occupies an enormous volume. Halo stars are overwhelmingly old, among the oldest stars in the galaxy, with ages of 10 to 13 billion years. They have very low metal content, some of them containing less than 1/10,000th the heavy element abundance of the Sun, indicating that they formed from nearly pristine gas in the early universe before many generations of stars had lived and died and enriched the interstellar medium with heavier elements. The stellar halo also contains the globular clusters that Shapley used to determine the Sun's position. About 150 to 200 globular clusters are known, each one a dense spherical collection of hundreds of thousands to millions of old stars, gravitationally bound and orbiting the galaxy on elongated paths that carry them far above and below the disk. Some of these clusters are among the oldest objects in the universe, with ages approaching 13 billion years, formed only a few 100 million years after the Big Bang. They are fossils, relics of the galaxy's earliest epoch, and studying them tells us about conditions in the universe when it was young. The halo is not smooth. It is riddled with streams and structures, the debris of smaller galaxies and globular clusters that have been torn apart by the Milky Way's tidal forces over billions of years. These stellar streams are like contrails in the sky, elongated arcs of stars that trace out the orbits of their destroyed parent objects. The Sagittarius stream is the most prominent, a river of stars that wraps around the entire galaxy, the remains of the Sagittarius dwarf galaxy being slowly digested by the Milky Way. The discovery of these streams, primarily through large sky surveys and the Gaia mission, has revealed that the Milky Way has been a cannibal throughout its history, growing by consuming smaller galaxies and incorporating their stars into its own halo. This process continues today and is a fundamental aspect of how galaxies grow in the standard cosmological model. But the visible components of the Milky Way, the stars, gas, dust, the bulge, the disk, the halo, all of it constitute only a small fraction of the galaxy's total mass. The Milky Way, like every other large galaxy we have studied, is embedded in an enormous halo of dark matter that extends far beyond the visible galaxy, perhaps to a radius of 1,000,000 light-years or more. This dark matter halo contains roughly 10 times more mass than all the visible matter combined. The total mass of the Milky Way, including dark matter, is estimated at about 1 to 1.5 trillion solar masses. The visible matter, stars and gas and dust, accounts for only about 60 to 100 billion solar masses, with stars making up the bulk of that. The rest, the overwhelming majority, is dark matter, invisible, undetectable by any telescope, known only through its gravitational influence on the things we can see. The evidence for the Milky Way's dark matter halo comes from the same type of observation that Vera Rubin made for other galaxies in the 1970s, the rotation curve. Stars and gas in the outer Milky Way orbit the galactic center faster than they should based on the visible mass alone. The rotation curve does not decline with distance as expected. it remains flat or even rises slightly. Out to the farthest distances we can measure, this means there is mass out there, enormous amounts of it, that we cannot see. The dark matter halo is not concentrated in the disk or the bulge. It forms a roughly spherical distribution, densest near the center and thinning outward, extending far beyond the visible galaxy in every direction. We live inside it, we orbit through it, and we have no idea what it is made of. Now let me give you a sense of where we are within this structure, because our location matters. It shapes what we see when we look at the sky, and it may have shaped the conditions that allowed life to develop on Earth. The Sun is located in the disk of the Milky Way, about 26,000 light-years from the galactic center, roughly halfway between the center and the visible edge. We sit near the inner edge of a relatively minor spiral arm called the Orion Arm, or sometimes the Orion Spur, a structure that lies between the more prominent Sagittarius arm, closer to the center, and the Perseus arm, farther out. The Orion arm is about 30,500 light-years across and roughly 10,000 light-years long, and it contains many of the bright stars and nebulae that dominate the night sky as seen from Earth. The Great Orion Nebula, a stellar nursery about 1,300 light-years away, is in our arm. So are the bright stars of the Orion constellation, the Pleiades cluster, and the Cygnus star-forming region. When you look at the night sky and see the familiar constellations, you are mostly seeing stars within the Orion arm, your immediate cosmic neighborhood. The Sun is located about 65 light-years above the mid-plane of the disk, a trivial distance compared to the disk's thickness. It orbits the galactic center at a speed of about 220 kilometers per second, completing one full orbit in roughly 225 to 250 million years, a period sometimes called a galactic year. The Sun has completed about 18 to 20 orbits since its formation 4.6 billion years ago. Each orbit carries us through different regions of the galaxy, past different spiral arms, through environments of varying density and star formation activity. The last time the Sun was at this point in its orbit, dinosaurs had not yet evolved. The time before that, the most complex life on Earth was multicellular organisms in the oceans. The galactic year is a humbling unit of time. As the Sun orbits, it also oscillates vertically, bobbing up and down through the disk like a horse on a carousel. The period of this vertical oscillation is about 60 to 70 million years, much shorter than the orbital period. The Sun passes through the midplane roughly every 30 to 35 million years, and some researchers have speculated that these passages through the denser midplane, where molecular clouds and other hazards are concentrated, might correlate with periods of increased impact events or mass extinctions on Earth. The evidence for this correlation is disputed and far from conclusive, but the idea that our galactic orbit might influence conditions on Earth is a fascinating example of how astronomy connects to biology. Our location in the galaxy may be significant in another way. The concept of a galactic habitable zone, analogous to the habitable zone around a star, was proposed by Guillermo Gonzalez and others in the early 2000s. The idea is that life is more likely to arise and persist in certain regions of the galaxy than others. Too close to the galactic center, and the environment is hostile, the density of stars is high, increasing the frequency of close stellar encounters that could disrupt planetary orbits and gravitational perturbations that could send comets raining into the inner solar system. Supernovae are more frequent near the center, and their radiation could strip the atmospheres of nearby planets or damage the ozone layers that protect surface life. The central region also has higher levels of background radiation from the supermassive black hole and from the dense concentration of energetic sources too far from the center, and a different problem arises. The outer galaxy has lower metallicity, meaning the interstellar gas contains fewer heavy elements. Stars and planets that form from this metal-poor gas will have less iron, less silicon, less carbon, less oxygen, fewer of the elements that make up rocky planets and the complex molecules of life. There may not be enough raw material to form terrestrial planets at all, or the planets that do form may be too small to retain atmospheres. The galactic habitable zone, if it exists, is thought to be a ring-shaped region in the disk, perhaps between about 20,000 and 30,000 light-years from the center. The Sun sits squarely within this zone. Whether this is a coincidence or a prerequisite for our existence, whether life requires a galactic address in this particular neighborhood, remains an open question. The concept of a galactic habitable zone is not universally accepted. The galaxy is a dynamic place. Stars move, environments change, and a planet's habitability depends on far more than its galactic location. But the idea is intriguing, and it connects the largest scales of cosmic structure to the most intimate question of all. Why are we here? Let me tell you about the stars themselves. Because the Milky Way is, above all else, a collection of stars, and the number of stars it contains is a number that resists comprehension. The current best estimate is between 100 billion and 400 billion stars. The uncertainty is large because we cannot see most of the galaxy's stars directly. The faint, cool, red dwarf stars that make up the vast majority of the stellar population are too dim to be detected at large distances, and the interstellar dust that permeates the disk blocks our view of distant regions. The estimates rely on models that extrapolate from the stars we can see to the total population, accounting for the luminosity function, the distribution of stars by brightness, and the fraction that are too faint to observe. Different assumptions yield different totals, but the order of magnitude is clear: hundreds of billion. The vast majority of these stars, perhaps 70 to 80%, are red dwarfs, stars less than half the mass of the Sun, cool and dim, glowing with a feeble reddish light. The nearest star to the Sun, Proxima Centauri, 4.24 light-years away, is a red dwarf so faint that it is invisible to the naked eye despite being the closest star in the sky. Red dwarfs are the most common type of star because the process of star formation favors low-mass objects. When a cloud of gas collapses and fragments, it produces many more small pieces than large ones, just as smashing a rock produces many more small fragments than big ones. Red dwarfs are also extraordinarily long-lived. Because they burn their hydrogen fuel so slowly, a red dwarf with half the Sun's mass can shine for trillions of years, hundreds of times longer than the current age of the universe. Every red dwarf that has ever formed is still shining today. None has yet had time to die. At the other extreme are the massive luminous blue stars, objects 10 or 20 or 50 times the mass of the Sun, blazing with a light millions of times brighter. These stars are rare, accounting for less than 1% of the stellar population, but they dominate the appearance of the galaxy because of their extreme luminosity. The bright stars that trace out the spiral arms, the stars that illuminate the great nebulae, the stars that will eventually explode as supernovae and scatter their enriched material into space. These are the massive stars. They live for only a few million years, sometimes less, burning through their hydrogen at a prodigious rate. A star with 50 times the Sun's mass shines about 100,000 times brighter and exhausts its fuel in about 3 million years compared to the Sun's 10 billion year lifetime. Massive stars live fast and die violently, and in their deaths they create the heavy elements that make rocky planets and living things possible. Between these extremes lies a continuous spectrum of stellar types, from sun-like stars that shine for billions of years with moderate luminosity to orange and yellow dwarfs, slightly cooler than the Sun. Each type has its own characteristics, its own lifetime, its own evolutionary path. The study of stellar populations, how many stars of each type exist in different regions of the galaxy, how their properties vary with location and age, is one of the fundamental tools of galactic astronomy. It tells us about the history of star formation in the galaxy, about the chemical evolution of the interstellar medium, about the processes that have shaped the Milky Way into its present form. The Milky Way is not forming stars as vigorously as it once did. The current star formation rate is estimated at about 1 to 3 solar masses per year, meaning that the total mass of new stars created each year is roughly 1 to 3 times the mass of the Sun. This sounds like a lot, and in human terms it is, but for a galaxy containing hundreds of billions of stars, it is a trickle. The Milky Way's star formation rate has been declining for billions of years as the available gas supply has been gradually consumed. The galaxy still contains substantial gas reserves, perhaps 5 to 10 billion solar masses of molecular hydrogen in the disk, concentrated in giant molecular clouds that are the nurseries of new stars. But this gas is being converted to stars faster than it is being replenished by infall from the intergalactic medium, and eventually, billions of years from now, the gas will run out and star formation will cease. The galaxy will age and redden as its remaining stars evolve and die without being replaced, transitioning from a vibrant spiral to a quieter, redder system. But the Milky Way's future holds something more dramatic than a slow fading. In about 4.5 billion years, give or take a few hundred million, the Milky Way will collide with the Andromeda Galaxy. Andromeda, also known as M31, is the nearest large galaxy to the Milky Way, currently about 2.5 million light-years away. It is slightly larger than the Milky Way, containing perhaps 1 trillion stars, and it is approaching us at about 110 kilometers per second. This has been known for over a century. What was not known until relatively recently was whether Andromeda's motion was aimed directly at us, or whether it would pass by at a safe distance. In 2012, a team using the Hubble Space Telescope made the most precise measurement yet of Andromeda's sideways motion, its tangential velocity, and concluded that the two galaxies are on a nearly direct collision course. The encounter is essentially inevitable, but the word collision is somewhat misleading. When galaxies collide, the stars within them almost never hit each other. Stars are incredibly small compared to the distances between them. If you scaled the Sun down to the size of a grain of sand, the nearest star would be another grain of sand about 4 miles away. Even when two galaxies pass through each other, the space between stars is so vast that the probability of any two stars colliding is negligible. The stars will simply sail past each other, rearranged by the changing gravitational field, but physically unscathed. What will change is the overall structure. The gravitational interaction between the two galaxies will distort their shapes, pulling out long tails and bridges of stars, triggering bursts of star formation as gas clouds are compressed, and eventually merging the two spirals into a single, larger, probably elliptical galaxy. Simulations of the merger show a complex dance lasting about 2 billion years from first close approach to final coalescence. The two galaxies will pass through each other, separate, fall back together, pass through each other again, and gradually merge. The spiral arms will be destroyed. The organized rotation of the disk will be scrambled into the random orbital motions characteristic of an elliptical galaxy. The result, sometimes called Milkomeda or Milkdromeda, will be a single large elliptical galaxy, a vast, featureless cloud of stars orbiting in all directions with no disk, no spiral arms, no organized structure. The Sun, if it still exists at that point, will almost certainly survive the merger. Individual stars are not threatened by galaxy collisions, but the Sun's position within the resulting galaxy could be very different. Simulations suggest there is a small probability that the solar system could be flung into the outskirts of the merged galaxy by the changing gravitational field, or even temporarily ejected into intergalactic space before falling back in. The night sky, if there's anyone on Earth to see it, and there almost certainly will not be, because the sun will be in its red giant phase and will have rendered Earth uninhabitable long before the merger is complete, would look completely different. The graceful band of the Milky Way would be gone, replaced by the diffuse glow of an elliptical galaxy. The familiar constellations would have been scrambled billions of years earlier by the sun's own motion through the galaxy. The sky would be full of stars, but arranged in no pattern recognizable to any being that had ever lived on Earth. The Milky Way is not alone in its corner of the universe. It is the largest member of a small collection of galaxies called the Local Group, which contains about 80 known galaxies within a volume roughly 10 million light-years across. Andromeda is the other major member. The third largest galaxy in the Local Group is the Triangulum Galaxy M33, a smaller spiral about 2.7 million light-years from the Milky Way. The rest are small, most of them dwarf galaxies, faint collections of a few million to a few billion stars orbiting the Milky Way or Andromeda as satellites. The Milky Way has at least 50 known satellite galaxies, and the number continues to grow as deeper surveys discover ever fainter systems. The largest and most famous are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as detached patches of the Milky Way's light. The Large Magellanic Cloud is about 160,000 light-years away and contains about 10 billion stars. The Small Magellanic Cloud is about 200,000 light-years away and is smaller. Both are irregular galaxies, lacking the organized spiral structure of the Milky Way, and both are currently interacting with the Milky Way gravitationally. A stream of hydrogen gas called the Magellanic Stream trails behind them, stripped from the clouds by the Milky Way's tidal forces, stretching across more than 100 degrees of sky. The Magellanic Clouds are likely on their first close approach to the Milky Way, having fallen in from a greater distance relatively recently in cosmic time. The smallest satellite galaxies are barely galaxies at all. Ultra-faint dwarfs like Segway 1 and Tucana 2 contain only a few hundred or a few thousand stars and are so dim that they were not discovered until the last 2 decades, found as faint statistical overdensities in deep sky surveys. These tiny galaxies are thought to be the most dark matter-dominated objects in the universe, systems where the ratio of dark matter to visible matter is hundreds or even thousands to 1. They may be the remnants of the smallest dark matter halos that were able to form any stars at all in the early universe, surviving to the present day as ghostly, nearly invisible companions of the Milky Way. Studying them is crucial for understanding how dark matter behaves on small scales, and whether the predictions of our cosmological models match reality in the most extreme environments. The Milky Way's environment extends beyond the Local Group. The Local Group is itself a member of a larger structure called the Virgo supercluster, a collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo supercluster is centered on the Virgo cluster, a massive concentration of about 1,300 galaxies, roughly 54 million light-years from the Milky Way. And in 2014, a team led by Brent Tully published a study defining an even larger structure called Laniakea, from the Hawaiian words for immense heaven. Laniakea is a supercluster of superclusters, a vast basin of gravitational attraction spanning about 520 million light-years, containing about 100,000 galaxies. The Milky Way sits in one corner of this enormous structure, pulled gently toward the center by the collective gravity of everything within it. But let me bring us back home, back to the galaxy itself, because there are aspects of the Milky Way that are not just scientifically interesting, but genuinely profound. Consider the interstellar medium, the stuff between the stars. Far from being empty, the space within the galaxy is filled with gas and dust in various forms. Hot, ionized gas at millions of degrees fills most of the volume, creating a diffuse medium that glows faintly in X-rays. Warm, neutral hydrogen at thousands of degrees fills large regions detectable by its characteristic radio emission at a wavelength of 21 centimeters. Cold, dense molecular clouds, with temperatures just a few degrees above absolute zero, huddle in the spiral arms, opaque and dark, collapsing slowly under their own gravity to form new stars, and threading through everything are magnetic fields, cosmic rays and radiation from stars and supernovae, all interacting in a complex ecological system. The interstellar medium is not static. It is churned and stirred by the energy released by massive stars. Stellar winds from hot stars push surrounding gas into expanding bubbles. Supernovae blast bubbles of hot gas that can be hundreds of light years across, sweeping up surrounding material into dense shells. These shells fragment and collapse, forming new stars which eventually explode as supernovae themselves, driving more bubbles. The cycle continues, each generation of stars enriching the interstellar medium with heavier elements forged in their cores and scattered by their deaths. This is the galactic ecosystem, a cycle of birth, death, and rebirth that has been turning for more than 13 billion years, steadily increasing the metal content of the gas and building up the complex chemistry that eventually produced planets and life. The chemical evolution of the Milky Way is written in the compositions of its stars. The oldest stars, formed from nearly pristine gas in the early universe, contain almost no elements heavier than helium. These population II stars, as they are called, are found primarily in the halo and the bulge. Their spectra show only the faintest traces of iron, carbon, and oxygen, reflecting the composition of the gas from which they formed, gas that had been enriched by at most one or two previous generations of stars. The youngest stars, formed recently from gas that has been processed through many stellar generations, contain much higher proportions of heavy elements. The Sun, a relatively young star at 4.6 billion years old, has a metal content about 50 times higher than the oldest stars in the halo. The most recently formed stars are even more enriched. Each generation of stars adds its contribution to the interstellar medium, building up the chemical complexity that makes rocky planets, organic molecules, and living things possible. There is a particular element whose abundance in the galaxy tells a remarkable story: iron. Iron is the endpoint of stellar nucleosynthesis in massive stars. It is the heaviest element that can be produced by fusion in a stellar core with a net release of energy. Beyond iron, fusion absorbs energy rather than releasing it, which is why iron accumulation in the core triggers the collapse and supernova explosion of massive stars. But iron is also produced in large quantities by type Ia supernovae, the thermonuclear explosions of white dwarf stars in binary systems. Type Ia supernovae operate on a longer timescale than core collapse supernovae because they require a white dwarf to accumulate mass from a companion, a process that can take hundreds of millions or billions of years. This means that the iron enrichment of the interstellar medium follows a different timeline than the enrichment by elements like oxygen and magnesium, which are produced primarily by core collapse supernovae of short-lived massive stars. The ratio of oxygen to iron in a star's atmosphere therefore acts as a clock, telling you something about when that star formed relative to the onset of type Ia supernovae in its environment. Old stars formed before many type Ia supernovae had occurred have high oxygen to iron ratios. Younger stars formed after billions of years of iron production by type Ia supernovae have lower ratios. By measuring these abundance ratios in large samples of stars, astronomers can reconstruct the chemical enrichment history of different parts of the galaxy. piecing together when and where stars formed and how the galaxy evolved over cosmic time. The Milky Way is in this sense a laboratory for studying the chemical evolution of the universe, with each star serving as a fossil record of the conditions that prevailed when and where it was born. The Gaia Space Telescope has revolutionized our understanding of the Milky Way more than any other single instrument in history. Launched by the European Space Agency in 2013, Gaia orbits the Sun at the L2 Lagrange point and has been measuring the positions, distances, motions, and physical properties of nearly 2 billion stars with extraordinary precision. Its third major data release in 2022 provided three-dimensional positions and velocities for more than 1.4 billion stars, along with information about their temperatures, luminosities, compositions, and variability. The dataset is so rich and so detailed that it has enabled discoveries that would have been impossible just a decade ago. Gaia has mapped the spiral arms of the Milky Way with unprecedented clarity, revealing that the arms are more complex, more fragmented, and more dynamic than simple models suggested. It has discovered dozens of new stellar streams in the halo, the debris of destroyed satellite galaxies and globular clusters. It has identified the remnants of the Gaia-Enceladus merger, a collision with a substantial galaxy that occurred 8 to 10 billion years ago and whose debris now constitutes a significant fraction of the inner halo. It has revealed the complex phase space structure of the disk, showing that the disk is not in a smooth, settled state, but is still ringing and sloshing from past gravitational disturbances. It has measured the acceleration of the solar system due to the galaxy's gravitational field, directly detecting the pull of the Milky Way on our local neighborhood. It has discovered thousands of new binary star systems, new exoplanet candidates, new variable stars, and new stellar objects of every kind. Gaia has given us for the first time a truly three-dimensional dynamical map of a significant fraction of the Milky Way, and astronomers will be mining its data for decades. Let me tell you one more thing about the Milky Way that connects everything together. The galaxy is old. The oldest stars in the halo and the globular clusters have ages approaching 13 billion years, meaning they formed when the universe itself was less than 1 billion years old. The Milky Way has existed in some form for nearly the entire history of the universe. It was not built all at once. It assembled itself over billions of years through a combination of internal star formation and external accretion, consuming smaller galaxies and incorporating their stars, growing larger and more massive over cosmic time. The earliest phase of the galaxy's formation is still poorly understood. The first stars, sometimes called population 3 stars, formed from the pristine hydrogen and helium produced in the Big Bang, with no heavier elements at all. These stars are thought to have been very massive, perhaps hundreds of times the mass of the Sun, and very short-lived, burning through their hydrogen in just a few million years before exploding as supernovae and seeding the surrounding gas with the first heavy elements. No population 3 star has ever been observed. They are a theoretical prediction, supported by simulations but not yet confirmed by observation. Finding one, or finding the chemical fingerprint of one in the atmosphere of a later generation star, would be one of the most important discoveries in stellar astronomy. These hypothetical first stars are the ancestors of everything, the first link in the chain of stellar generations that produce the elements in your body. After the first stars enriched the primordial gas with a smattering of heavy elements, subsequent generations of stars formed with gradually increasing metal content. The galaxy assembled through a combination of smooth accretion of intergalactic gas and mergers with other protogalactic fragments. The halo and bulge formed first, or were assembled from the merging of many small early systems. The disk formed later as gas settled into a rotationally supported structure and began forming stars in a more orderly fashion. The spiral arms developed as density wave instabilities in the disk. The bar formed through dynamical instabilities in the inner disk. Each component has its own age, its own chemical signature, its own kinematic properties, and together they tell the story of the galaxy's assembly over 13 billion years. The Milky Way today is a snapshot in a long evolutionary process. It was different 1 billion years ago. It was very different 5 billion years ago. It was almost unrecognizable 10 billion years ago. And it will be different again in 1 billion years and transformed beyond recognition in 5 billion years when Andromeda arrives. Galaxies are not static objects. They are processes, ongoing events that unfold over timescales that make human history look like the flash of a camera. And yet here we are inside this process, made of its materials, orbiting its center, looking outward through its dust and gas and stars at a universe that contains 2 trillion more galaxies just like it. Every atom in your body has been part of this galaxy for at least 4.6 billion years, since the Sun and its planets formed from a cloud of gas and dust in the Orion Arm. Some of those atoms have been part of the galaxy for much longer, recycled through multiple generations of stars. The carbon in your DNA may have been fused in the core of a star that exploded 8 billion years ago, spent 4 billion years drifting through the interstellar medium, was incorporated into the molecular cloud that formed the Sun, ended up on a planet orbiting that Sun, and is now temporarily part of a living thing that is contemplating the galaxy that made it. You're not in the Milky Way the way a fish is in the ocean or a person is in a building. You're not a separate thing contained within a larger thing. You are made of the Milky Way. Your atoms are galactic matter, temporarily organized into a pattern that can think and wonder and ask questions. When you look up at the night sky and see that faint band of light, you're not looking at something other. You're looking at the rest of yourself, scattered across 100,000 light years, glowing with the light of hundreds of billions of stars, held together by the gravity of dark matter that no one understands, orbiting a supermassive black hole that anchors the entire structure, participating in a process that began 13 billion years ago and will continue for trillions of years after the last. Trace of your existence has been erased. The Milky Way is not just where you live, it is what you are. And the fact that a small collection of its atoms has arranged itself into a being capable of knowing this, of mapping the galaxy's structure, of measuring the mass of its central black hole, of tracing the orbits of its stars and the streams of its consumed companions, of predicting its collision with Andromeda 4 billion years in the future. This fact is, when you sit with it long enough, the most astonishing thing about the entire galaxy. The band of light is still there, arching across the sky on every clear dark night, just as it was when the first humans looked up and wondered what it was. We now know the answer, or at least a version of the answer that is far more detailed and far stranger than any myth ever conceived. It is a barred spiral galaxy, 100,000 light years across, containing hundreds of billions of stars and trillions of planets, embedded in a halo of invisible matter, orbiting a central black hole, assembling itself through cosmic cannibalism, heading toward a collision with its nearest large neighbor. It is ancient, dynamic, violent, beautiful, and home. It is the Milky Way, and you have never left it. No human ever has, no human ever will, but you can look at it, you can study it, you can know it, as well as any arrangement of atoms can know the structure that made it. And that knowing, that improbable, temporary, extraordinary knowing, is what makes the galaxy worth contemplating. Not because it needs to be known, but because we can know it, and because the act of knowing connects us in the deepest possible way to the thing we are trying to understand. The stars are burning, the disk is rotating, the dark matter is holding everything together, the black hole is waiting. The dust is drifting between the stars. carrying the atoms of dead suns toward the birthplaces of new ones. And somewhere in the Orion Arm, on a small rocky planet orbiting an average star, a species that has existed for less than a millionth of the galaxy's lifetime is measuring the shape of its home and finding it beautiful. The Milky Way does not care. It is not aware. It does not know it is being studied, but it made the thing that studies it. And that is enough. That is, when you think about it for long enough, everything